The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, and thank you for joining us on our call today. My name is Nicole Van Wert Quincy from Transcat, and I'll be your moderator this afternoon. Our webinar topic is how to calibrate an IR thermometer. The topic is being presented by Travis Porter from Fluke Calibration. Travis has been with Fluke Calibration for 20 years and has served in a variety of roles, including manufacturing, technical support manager, and his current role of inside sales account manager. We expect today's presentation to last roughly 30 minutes, and then we'll open it up for questions and answers at the end. During any time of the presentation, you can send questions through the question box, which is located in the right side of your webinar controls. I also want to mention that the webinar is being recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. And at this time, I'm going to turn the presentation over to Travis.
All right, welcome everybody. We'll just jump right into it. Today's presentation again is just a pretty basic run through on how to calibrate a IR thermometer. There are a few pieces of this presentation as we go through. You'll see there's spots that may involve further discussion, especially kind of around the uncertainty analysis. We're not going to dig real deep on that. But if you do have questions, I've included our guru on my side of the fence, Frank Liebman's information. He's kind of our IR expert. He worked with us on developing our products in engineering. He sits on the ASTM board for the infrared piece of it. He does answer emails. We'll get to them. He's not very quick to that because he is in high demand. But if you do have additional information where we didn't get to dig in very deep, he's the guy to kind of go after there. And again, it may be a minute, but he will get to you. So again, here's kind of just a basic outline. We're going to do a quick, rundown of introduction, sources of uncertainty, kind of the calibration equipment, some traceability schemes. Most of that's going to be based around my current process in our lab here, in our laboratory setup. We'll kind of give you a basic rundown on a calibration procedure, what a basic uncertainty analysis looks like, and kind of what's required to report on your side of the fence when you kick out a calibration report. All right, so just a quick introduction. IR thermometry can be fairly accurate. Again, it's not as accurate as some of the other techniques in temperature, such as when you're using SPRTs or PRTs or contact calibration, but it's coming along. Anytime you are using infrared, proper procedures and usually consistent procedures would be the more proper way I would state it as far as what you do and are following each time you do it. Currently, the ASTM E2847 is kind of the standard practice out there. So again, if any of you are interested in more, again, ASTM's got a wide variety of different things they've got information on. So basically what ASTM stands for is the American Society for Testing and Materials. Basically, there's a lot of volunteers that work together that post, best practices, white papers, studies on, basically subject matter that they're the experts in. So again, that's a good place to look if you're looking for more, or we kind of skim by something you want to dig in on. All right, so we're going to first look at our sources of uncertainty and kind of go through these different pieces here. So your major source of uncertainty, excuse me, first and foremost is going to be your calibration source. So I don't know what you're using out there. Some people, you'll hear the terminology of black body, gray body, IR cavity. All of these are going to have a different uncertainty associated with them based on if they're homemade, if they're manufactured, what the OEM specs are. So again, that's something really to consider. And again, on about the first three of these, so then we jump down to kind of the field of view of the actual infrared thermometer you would be testing, and then temperature gradients on the radiation source. Most of this information should be able to be sourced from the OEM or your user's guide on the pieces of equipment. Some of the other things you really need to consider when working with a infrared gun is the alignment. So a lot of times you'll have infrared guns that do have laser pointers on these. those laser pointers get you in the general area. The laser pointer is not the actual optics. Again, that's just a tool built in most of the time to help you kind of get a good bead on the area you're working with when you're taking a measurement. Then we come down to the calibration, the radiation source. So again, I guess I misspoke. So there's the calibration temperature of the radiation source and then your emissivity estimation. So again, the calibrated temperature should come with the unit OEM. Usually it's expressed in a tolerance of a plus minus with an uncertainty associated to it. And then the emissivity estimation is usually stated on also the cal report. So an example here for our black bodies we sell, we state a 0.95 emissivity. And usually on a lot of the guns out there, you will see them spec to, yeah, this is a 0.95 IR gun on the optics. So again, matching those up does become critical in the process. Some of the other things to consider is your environment where you're performing the testing. So ambient temperature, typically you want to be in a laboratory type controlled environment. Usually most labs run a typical spec of 23 plus or minus 5. I do know on the mass and dimensional labs, they're usually 21 plus or minus 3. So again, you're wanting to be in a good controlled ambient environment. And then two, we'll talk a little bit more further on this reflected temperature. So again, you have to remember that the IR optics are, they're designed to see emitted energy that our eyes can't see. So again, if you think of it, don't know if you're big film fans, I grew up kind of in the late 80s, so I think of this best way is like the Predator with Arnold Schwarzenegger. That's what the optics of the IR gun are going to see, and then kind of put back, and we go through the electronics and spit out a temperature for us. Some of the minor sources, source heat exchange, usually that's if you've got like the unit set up against where there's a fan or there's something else that can affect or add to the stability. So again, if you had your heat source set up under, say, a vent in the ceiling, you could potentially have some problems there. Atmospheric absorption is another one. We'll kind of show an example of that. And then just noise. Noise usually can be reduced using a partition or making sure you've got a good distance to spot size ratio, and then to just your display resolution. So again, with if any temperature reading in general, resolution does not mean accuracy. So again, be aware of that. Most people think more resolution, more accuracy. No, it means basically more noise at some point, not more accuracy. All right, so next in line, we're gonna kind of get into the calibration equipment or the hardware piece of it. And I apologize if you hear some paper. I've got my hard copy here that I make notes on. So you'll hear that flipping in the background. All right, so the mandatory equipment, you definitely have got to have a heat source. Again, this is gonna be your IR cavity, gray body, black body, something that is gonna emit, and then a transfer standard. These can be a couple of different things. So as we get further into this discussion, we're going to kind of show us scheme 1 and scheme 2 on our transfer standards. One's basically taking contact to IR and the other one's taking IR all the way. So again, with your transfer standard, you've got to have some sort of calibrated standards, maybe a control probe, or it could be another calibrated IR gun that's at a higher level. In-house, when we do our radiometric calibrations, we use these guns that are called KT-19s. They're very high end, and then we calibrate those. And again, we'll dig into that a little bit. But again, that's the transfer standard from us going from the radiometric of the gun to the radiometric calibration of our black body. Mounting device, I guess this shouldn't be quite mandatory. It should be kind of non-mandatory, but depending on how critical your measurement is, again, a mounting device is really good, like a tripod. A lot of handheld IR guns do have a spot where you can screw these into a tripod. What this allows you to do again is get a very good measuring setup, and we'll show some pictures of that here shortly. Again, this all comes down to with the infrared guns, usually there's a distance to spot size ratio that you want to maintain, and you want to then be consistent if you're performing, say, several calibrations on the same type of guns. Usually the specs are the same. Non-mandatory, we talk about a purge cavity. I'll get into this a little bit later. Basically, usually it is relevant only to subambient IR work. So when you're working below ambient, obviously you're going to run the risk of drawing moisture from the air to your target. So there's a few techniques that you can use to keep that from happening. A good part about that is IR measurements are fairly instantaneous. So again, not difficult, even if you have to kind of cool your plate down, remove the cover, take your readings, put the plate back to keep this frost buildup. The frosting can actually impact the emissivity reading. So just going into kind of sources that I'm going to be mostly talking to you, these are the products that we offer, 4180 and 81. Basically, we have a hot unit and a subambient unit. They're a flat plate design, again, but some other units that we have are a cavity design. So again, these are just the sources in the process. So it's going to heat up, become stable for us, and that's what we're going to take a measurement from using our IR gun. All right, so we talk about, over the years, I've seen a lot of, I guess I should say, change or different styles of different heat sources. We do have another line with smaller targets. With this one, we went kind of with the bigger one. It was kind of a jump up. We do calibrate these to 17025. So again, we were kind of trying to provide a heat source that is also a standard. So for that, to achieve that, we went with the larger 5-inch targets. This gives you a really good range when it comes to distance to spot size, so you've got a lot of area to work with. So again, the example on the right here, that was one of our kind of first gen ones. We used to have a really small 9131 product, but again, the IR target was really small. So again, depending upon how small, based on the distance, you could get that spot size of your IR, it may or may not been a good radiation source. Basically, if I look back on it over the years, the small one would have been probably applicable for a great quick check, not an actual calibration source. So again, always look at the manufacturers, consult them if you have questions before you start getting into your testing and working through the setup. So we're going to go through a couple of schemes here that I mentioned as far as contact thermometry versus non-contact. And we're kind of going to show you how we do it internally through our lab. So again, obviously contact thermometry is referencing back to we've got something actually physically touching. Usually it's right behind the black body surface, or in a cavity situation, it's touching right up against the point of the cone internally. In a non-contact thermometry, which we're going to call scheme 2, it's all done through radiation only. So you're basically, everything is being done with the optics of an IR. So again, we'll have a little bit more under this, the traceability schemes that we're going to touch on. I'm trying to think here. As far as implementing, again, it can be an internal requirement. It could be that you're a third-party lab and you're going to have a scheme that you need to present for auditing purposes. So again, the implementation kind of comes down to, hey, am I just quick checking these for my guys on the floor, or I'm a third-party lab and I'm trying to go for ISO accreditation. So again, how in-depth your scheme or process needs to be depends on what you're looking to accomplish in the setup there. So as we go through the process for setting up a lab environment, and I'm going to look back here really quick. So this is going back to our laboratory setup. you want to have a good source to monitor your ambient condition. So I made mention that most typical labs, you're around 23 plus or minus 5. Some of the more specific labs in you know, dimensional, and that they have it much tighter. So in-house we use a Duke unit. This monitors our temperature for the room and humidity. So again, this kind of gives you a good idea where your testing is set up. If there's something you may not be aware of, they might catch it, you know, as far as reflected radiation, or the ambient temperature may be fluctuating too much to be, you know, good in a process. And so that may mean that you have to move to a different location in the room. So an example, if again the process was set up directly under a heating or AC vent, you may see a great swing every time that kicks on and off, while the overall ambient temperature doesn't feel like it's fluctuating. Right in that space directly below it, you're going to see these fluctuations. So furthering down kind of in the setup, you know, mounting devices, again, we talked briefly about the tripod. I've seen them get as complicated as on some of them, where the high end on where they've actually got a cross table that moves, you know, on the X and Y axis, and then you can lock it into place. These are kind of custom fixturing. But again, if you're doing high volume, this would be more applicable to, say, third-party labs. You know, a setup like this may be advantageous because you're going to be able to quickly connect the IR gun, set the fixturing, lock it into place, and then, you know, say you've got 5 or 10 of these guns to do at a time. That's all set. You're good to go. You just start the testing process. So the very bottom there is a hand. So again, you can use your hand, but again, you're going to have to make a good estimation and come up with a good way of being consistent as far as your distance and height to relative to the target of the IR source. So again, this next slide here kind of shows an example of where you want to be. So ideally, you're going to be centered in your target. You're going to keep equal space between like equipment or like guns. So again, measuring rods, you know, or these devices such as tripods, different things, you can set them up, lock things into place. And again, that just allows you to perform more consistency in the actual readings that you're taking. So again, we talk on kind of some of that non-mandatory. So an aperture for frost dew prevention. If you guys have questions on that afterwards, we can show you how we're doing it. We don't dig too much into it in this presentation. On our 4180 unit, the actual target cover does have kind of a dry air purge system built into it, where you can basically take either dry shop air or dry nitrogen, run a tube over to it, connect it, and with a very, very low volume, basically just enough to get a positive pressure. It'll bleed through and keep a positive pressure on that target, preventing frost, versus if you were just to kind of pull it off and you know, run at say 5 degrees C in a 20 degrees C room. So again, things there can be done. On some of the bigger labs or different pieces of equipment, I've actually seen full-on purge boxes that press right up tight against the IR targets and kind of lock it in place there. So again, sometimes it is custom pieces of equipment that are used in the process. Okay, now we're going to touch on those traceability schemes that we kind of talked about. There was the 1 and 2, basically the contact, and then the radiometric. So again, here we've got them, scheme 1 on the left, scheme 2 on the right. Basically, now we're all talking in, you know, traceable to the SI, so it's the unit of measure. I think that's the new language everybody's using going forward. Most of the SI comes through your national lab, so the NMI. So in our scheme 1s, I think we've got a little bit more detail on the next slide. Yeah, so here we go through an example of scheme 1 we would have our fixed point cells calibrated at, say, NIST. This goes to be used in the process for our SPRTs. We use the SPRTs. There's several steps in between each one to calibrate our PRTs, but then we use the PRT to actually calibrate the IR source. So again, that's the contact. So we're actually physically touching the pieces of equipment as we go through this unbroken chain. In the scheme 2, again, now we're just using pure radiometrics. So the NMI is going to test our transfer standard gun. We're going to use that gun as the standard to then calibrate our radiation source. And then we're going to use that radiation source, which would be in this case the 4180X units, to calibrate our infrared guns. So again, I kind of went through this a little bit where the SI comes from the NIST or your national lab, usually in the form of fixed point cells. And again, when we talked way back at the beginning, IR is good, but it's not the best way to take measurement in temperature. There are other techniques, which is usually contact calibration, because we can go right to our fixed point cells, which provide, basically everybody's agreed, the lowest uncertainty, and everybody's agreed, for example, what the triple point of water is, how to achieve it, different things like that. One thing not shown here in the scheme is we actually kind of have a scheme 3. So we actually have a check standard in part of our scheme 2 process. So we have a gun that we calibrate using our IR process that we then send out to a independent national lab for them to check it, and it comes back to us and we compare the results. So again, depending upon where you need to be in the process again, or what you're looking to do in either the, say, a more industrial process or lab process, kind of depends on what you need to do within the setup for your traceability documentation. All right, so we're going to continue on. So again, laboratory setup, I think, is next. We kind of touched on this. The Duke, again, is going to monitor temperature and humidity. It's going to give us a known that we can add into the uncertainty analysis. Again, it can also alarm us as far as, you know, rapid changes in the ambient temperature or any reflected uncertainty. So again, the sensor would pick up on that. We would see the display change rapidly. That would give us a warning, hey, something's up or something has changed. So continuing on in the laboratory setup, these are just kind of some real basic tips on setting up units. You don't want to have units facing each other. Basically, you're going to be passing radiated energy back and forth. Again, we didn't really jump into emissivity, but it's kind of a percentage. So you want to think of it as basically 0% to 100%. So again, most things that we're talking with or working with are spec'd at what we would call 0.95 or 95%, meaning that it's emitting 95% of its energy. A perfect black body is described as 1, so you're going to get 100% of that emitted energy back out of it. So again, units facing each other basically could be, you know, the hot guy would be emitting, be like putting a hairdryer on an ice plate. You're going to have them fighting each other. Again, windows. Windows, you can actually get reflected energy, so you want to avoid those. And again, I've talked a couple of times too of getting too close to your HVAC type setups. We've actually a lab down the road from us, we worked with them, and they actually had to put a downdraft, updraft, you know, one in each corner to kind of pull the air in a specific direction through their lab to kind of help equilibrate it. So if you're using multiple ones, you know, it's recommended to keep them fairly far apart. 1 meter is about what we recommend, a few feet, and then isolate as much as we can from drafts in the room. Again, interior wall helps as well, because again, you're going to reduce any chance of emitting some large or radiated energy from, say, a window or something else. So again, sometimes I've actually seen in labs where if you go back to this example where they've actually had to put basically some sort of diffuser device, whether it be a kind of like an insulating material that kind of basically causes the airflow, instead of blowing out and straight down, it's going to hit that and blow again horizontal, and then spread the air out more uniformly. So again, just some tips here on that. In this example, again, I'm showing you kind of the use of a partition. Here you can see that we kind of go back to that measuring distance, measuring height. We're going to get our reading. The partitions can be used more so at lower temperatures. To test if, you know, the testing you're doing at lower temperatures is being, say, impacted by emitted energy that you're not seeing, you can build just a really simple partition set of cardboard or something and take your, you know, measurement again using a partition versus not using it. Again, you may find it not necessary, but if you do see a difference in your reading, there's a good chance that there's some radiated energy beyond the target that's impacting your readings that you're not aware of. So again, it's kind of a test it, see if you get a difference. Again, what the partition is doing is allowing basically noise or scatter. It's kind of limiting how much the optics can be impacted by that coming back in, by limiting the field of view up close. All right, so the next few points, again, we're not going to dig a whole lot into the details of these, but basically we're going to go into calibration procedure, talk a little about preparation, cal points, and then procedural. For the preparation, again, if you're a lab, usually you want to wait for the pieces of equipment, and this is just good practice with any electronics, have them on and going, or at least equilibrated to the room temperature. You wouldn't want something that just was received in from, say, shipping on a hot or cold day to go immediately into the lab. You grab it and take your readings. Lens cleaning, that's a tricky one. Some customers want you to do it, some don't. Usually you steer clear of it unless requested to. There's usually some pretty good specifics around that. If you go down that road, usually you're going to have some sort of process that involves specific lens wipes, usually camera wipes, of the kind that are non-residue, non-streaking, different things like that. Because again, you get grease, different things on the glass. It can goof your readings because again, basically it's like blinding the eye of the optics on that. So the setup, any special equipment, okay, we've touched on that again several times, going with your distance, your size upward, partitions, maybe a purge. Again, once you get all that going, then the next piece is simple. Once the actual measurements is the easy part of this process. You're going to set the black body to your desired temperature. You're going to allow it to come up to temp and stabilize, and then you're going to simply take your readings. So again, the good thing with our 4180 units, they do have a built-in alarm. You set your stability limit into that, and then it'll come up to temp, and when it's ready, it will beep at you and kind of let you know, hey, it's your audible, I'm ready to be used now. Kind of driving into calibration points. So this is a little bit of a subjective matter. So again, it can be determined by the customer. If you're doing it, say, on a shop floor or something, and you have a very specific process and you don't need to check the optics across the full range, you may do a limited range. So again, you could have differences in a wide to small range. You may only be checking 1 to 2 points. Again, calibration points and getting into the procedural piece of it, it's all about how you define the scope of what you're looking to do and what you're going to do to stay in compliance to that scope. With temperature in general, it's always best practice to go from your lowest calibration points to the highest. Just seems to net you the best results. And then two, typically with the heat sources, it's usually a much faster process to go from cold to hot versus vice versa, going very hot down to cold. So when you're setting them up, again, our targets on the 4180s are, calibrated at 0.95. The cool part about these is you can adjust the emissivity. There is a setting based on Planck's law in there where you can actually set it to say 0.3 or 0.93, 0.92, and it'll actually emit or correct the target temperature to emit that. So kind of a neat feature there. With your guns and your IR sources, you always want to make sure they're the same. So if you're testing a 0.95 gun, you want to make sure your heat source is a 0.95 source. Again, the alignment, we're doing the XY. The Z direction, I can't remember if I got a slide on that, but it's basically if you're doing it by, this is more applicable to hand alignment. Even though you've got your, your X and Y, your up and down, if you tilt in or out or left or right, that can cause a deflection in what the optics are going to see. So again, make sure you're level is a good way to put that. You want to make the optics up and level straight on to the target, so you're not, again, getting that deflection, and you're going to get a good, the entire optic is going to be looking at the source. So then you make your measurement. The fun part about IR measurements, it's not like some of the other temperature measurements where you have to wait. Once you pull the trigger on the gun, it's, again, fairly instantaneous. But even in the longer IR thermometer, say you have a response time of 0.5 seconds, maybe keep it held in there for 5 seconds, kind of just a rule of thumb. So again, and sometimes you'll want to take multiple readings and average them just to make sure you're not getting something that's going weird within the electronics of the gun. So again, we kind of, this slide again, and this is the one I was kind of touching on with the kind of the axis of, leaning in, down, left, right, you're going to cause some deflection. So again, you want to be straight on as best you can to get that consistency in the readings that you're taking. All right, so most guns are not adjustable. So usually, check the emissivity. So, and a lot of times when you're calibrating these, it can be just a pass-fail based on tolerance. So again, match it, make sure you're matching emissivity to emissivity. And then again, me personally have not adjusted one of these. I know there are some out there that are, but I think that usually is, most of the time from what I see, requires OEM. They usually have some sort of software that they don't hand out. So again, most of the calibrations I'm seeing done are a pass-fail. So now we're kind of showing you here a quick example. Again, I'm going to click back through of an uncertainty analysis. This is where we're not going to dig in too hard, but again, a lot of things to consider. You're going to have your source uncertainties as well as your thermometer uncertainties, and then there's these additional ones as far as can you reproduce it. So again, there's a lot of things that go into your uncertainty analysis, especially again, depending upon what you're looking to do. So again, if you're a third-party lab or an accredited lab, your uncertainty analysis are going to be much more complex, because you're going to have to be GUM compliant, and then again, being able to prove and show, an auditing trail, how I'm coming up with these numbers, how I can repeat these numbers. Versus again, if you're just say using the source, say a 4180X, and I'm using it as a quick source to check my guns that are used in my production process. All right. So again, we're going to jump to reporting your results. So this is just kind of a basic what would be required once you've done the testing, once you've compiled the data. For most reports, you're going to have a title, name, address, where you're at, usually a unique identification number of the thermometer and your sources, a method used. So again, as this contact, it goes back kind of to those scheme 1, scheme 2, obviously a date of calibration, and then statements. So if there's any exceptions, and if you were to look at, say, one of our calibration reports, we have statements about being, guard banding and K equals 2. So there's a lot of different things you can kind of touch on in your report if you think they're going to be a questionable, I guess, point to be argued. And then you're going to report your results. So again, are we, what are we versing? What is our uncertainty? Most reports, again, are going to show typically a set point, an actual, the reading, and then the error, and then usually a tolerance that we're testing to. It's also good, again, if you're doing repeated or establishing a kind of a history of different guns, you may want to have that in your database of, hey, for the, manufacturer X, 1, 2, 3, this gun gets a 6-inch distance from the target at a 2-inch height, and we take these data points. Again, to the emissivity setting of the infrared thermometer, usually of the, and you can also do that for the source as well, and then the diameter of the source. Again, the ones that are kind of tagged out here as stars, those are the ones that we have to include in our 17025. So again, depending upon where you're at in the process and what you're trying to accomplish in the process, will kind of define how stringent or what needs or doesn't need to be in the report. And then again, obviously our temperature and humidity of the ambient, which we talked on about using the Duke, any aperture inclusions or not, and then usually the person, usually it's the tech that did the actual work, and then an authorizing sign off on the report. So again, just a kind of a quick breakdown of kind of your basic reporting structure there. So again, I hope this was helpful. The main point we wanted to get across was to follow a consistent procedure, and depends, again, where you're at in the calibration cycle, whether it's more geared towards industrial or third-party cal. But again, consistency, having your knowns and unknowns well-defined is going to lead you for better, more consistent calibrations and happy customers that will hopefully lead to some repeat business. Again, here's Frank's information. So if there's something you want to dig in deeper on, again, he is our go-to guru for anything IR, and he's happy, again, to answer emails. He is, again, a little slow, but he will get back to you.
Okay.
All right, Nicole, back to you.
Perfect. All right. Thanks, everyone, for your time. And we're going to open it up for question and answers right now. So that's the conclusion of our presentation portion. As a reminder, if you'd like to submit questions, you can submit them in your webinar controls. It's in the right side of the webinar panel. And I've got some questions to start off with. We'll get right to it. So the first one, how do we find the distance spot size for the IR gun we are calibrating?
All right, so these are going to vary. Sometimes you're going to have to look in your OEM user's guide. Some of the guns, Fluke manufacturers will have a label on the side that shows this, and I do believe on some of the other ones, it's actually the distance to spot size is cast into the actual plastic housing on the unit. But again, if you're questioning it, always go to your OEM user's guide.
Okay. In your example of the partition at low temps, is it a requirement to use this?
No, this isn't a requirement. Again, this is just kind of a guard band if you think there might be some radiated uncertainty that's impacting your reading. So again, say there's I don't know, again, it goes back to the heat vent, but that's fairly obvious, but it could be, say, another heat source where it's emitting something. The best example is what we've done when we do our courses here is we'll run a unit down to, say, fairly low temp, say 15C, and then you can actually blow with like a heat gun a few feet away from it and just directly in front of it. And then if you try to take the measurement, basically the optics of the gun go out and they see that heat source from the heat gun in front of the target. So again, there's, you can't see that, your target's reading cold, why am I not getting a cold reading? So again, it's kind of that scatter and unseen noise that can kind of contribute to these little weird errors in the process. So again, you can make those quick checks if you think there's a problem, try it with and without, and if it's changing quite a bit, then there's usually something that's a source to that scatter or noise you're seeing.
Okay, are all IR guns set to a 0.95 emissivity?
So are all the IR guns set? No, that's just kind of the industry standard. I've seen some that are adjustable. So again, typically on the lesser expensive guns, they tend to have a fixed emissivity. The most common ones I've seen are the 0.95 and 0.93. I think in the steel industry, there's some that are much higher because where they're viewing the heat is at like molten metal, so it's a little bit higher. I can't remember if it's 9.8 or 9.2. There's something weird, but again, some guns are adjustable. But again, with our 418X series, we've got that built-in adjustment, so you can kind of fake out. Since we know our coating is 9.5, we can use Planck's law to kind of manipulate that emitted energy.
Okay, you mentioned a dry purge. Can you explain more about this?
Sure. So this is, again, used when calibrating sub-ambient temperatures. So you can't basically have anything out that's going or ambient. You're going to start drawing moisture from the air to that surface. So depending upon the setup, so for an example, in-house when we're doing our manufacturing process, we've got these custom purge boxes that we press the target or the machine finished product up against, and that provides a purged environment. If you don't have that, the best example is our 4180. We've kind of designed a hole in the front of the target cover that you can hook a small tube to, and then you can, I think it's like very, very low pressure. It's like point something PSI. And you basically can purge dry shop air if it's filtered or dry nitrogen. Again, so it's a low pressure because, again, you're just trying to keep the ambient air from coming through and then condensing on the target.
Okay, that looks like that's all of our questions for today. If you have further questions that went unanswered or you'd like to find out more about what Transcat's product and service offerings are, you can contact us at 800-828-1470 on the web at transcat.com, or you can definitely email me directly and I'll get answers for you, nvanwert@transcat.com. Thank you for joining us today. We hope you got something out of the presentation and that you continue to join us for future Transcat e-learning webinars. Have a great day, everyone, and thanks, Travis.
You're welcome. See ya.
See you.